Dear students, we shall continue Lagrange's equation. So solve the equation z into xp minus yq equal to y square minus x square. Now taking that z on the left side to the right side, we get the equation xp minus yq equal to y square minus x square by z. So this is in standard form of Lagrange's equation. Now to solve this equation, we have to write the auxiliary equation. So the auxiliary equation is nothing but dx by x equal to dy by minus y equal to dz by y square minus x square by z. Now comparing the first and second, we get the equation dx by x equal to dy by minus y, which is a variable separable equation. It can be solvable. So integrating, we get the left side is log x equal to, the right side becomes minus log y plus the constant of integration. That constant is taken as log c1, ln c1. Now taking minus ln y to the left side, we have ln x plus ln y equal to ln c1 implies log x into y equal to log c1 implies xy equal to c1. So this is the first part of the solution. Now we cannot apply the comparison method for the remaining ratios. Next we shall consider the Lagrange's multiplier method. So choosing the multipliers as 1, 1, 0, we get each ratio. We can write each ratio is equal to 1 into dx plus 1 into dy plus 0 into dz. That is nothing but dx plus dy in the numerator divided by 1 into x plus 1 into minus y plus 0 into that one. So we get the new ratio as dx plus dy by x minus y. Now we can equate this ratio to any one of our ratio of auxiliary equation. So we shall equating this new ratio to the last one. We have dz by y square minus x square by z equal to dx plus dy by x minus y. That is, we are equating this new ratio to the last ratio. We will get like this equation like this. Now this z come to the numerator. So z dz by y square minus x square equal to dx plus dy by dx minus dy. X minus y. Now from the left side, on the left side we have y square minus x square, which can be factorized into y plus x and y minus x. So z dz by y plus x into y minus x equal to dx plus dy by x minus y. Now cancelling common factors on left and right side, we have minus 1 either on left side or the right side. We can add this minus here. So minus z dz by y plus x equal to dx plus dy by 1, that is dx plus dy. Now cross multiplying, we have x plus y into dx plus dy equal to minus z dz. So x plus y into dx plus dy plus z dz equal to 0. Now we are multiplying by 2. We have 2 into x plus y into dx plus dy plus 2z dz is equal to 0. Now for integrating this one, taking the substitution x plus y equal to some u, then dx plus dy is equal to du. Therefore this equation becomes 2u du plus 2z dz equal to 0, which is a very simple differential equation. On integration, we will get the solution u square plus z square equal to c2. Replacing u by x plus y, we have x plus y the whole square plus z square equal to c2. Now expanding x plus y whole square, we have x square plus y square plus 2xy plus z square equal to c2. Now from the first part, we have got the equation, we got the answer xy equal to c1. So here we can substitute this xy as c1 on this equation. We have x square plus y square plus 2c1 plus z square equal to c2. That is x square plus y square plus z square equal to c2 minus 2c1. Put it as some c2 dash. This is now this x square plus y square plus z square and xy equal to c2 dash and xy equal to c1 are independent solution. If you are taking this one as c2, this is if we take this as the second part of the solution, here we have the 2xy. That means this is not these two. That means b and u are not linearly independent. So in order to make it as independent solutions, we are taking this xy, replacing this xy by c1 and proceed. Therefore, we get the second part of the solution as x square plus y square plus z square equal to some constant, say c2 dash. Therefore, the required solution is x square plus y square plus z square equal to function of x y. Understand? Yes. Now, can go to the next question. Before going to the next question, we are applying the continuation or the deduction of the property of algebraic ratio. There we have written that if a by b, a1 by b1 equal to a2 by b2 equal to a3 by b3, then another important property of this algebraic ratio is we can generate another set of equivalent ratios, that is a1 minus a2 by b1 minus b2. That means we are subtracting two ratios, the numerator difference of numerator and denominators. a1 minus a2 by b1 minus b2, that's equal to a1 plus a2 plus a3 by b1 plus b2 plus b3, or it is also equal to say a1 plus a2 by b1 plus b2, and also equal to a2 minus a3 by b2 minus b3, and so on. We can get we can generate any type of new ratios. The only thing is what we done in the numerator, that should be repeated in the denominator also. That is a important property. Now we are applying this property for solving the next equation. So second one, solve the equation px into x plus y equal to qy into x plus y plus y minus x into 2x plus 2y plus z. Now this is not in standard form because q term is on the right side. So we are taking this term to the left side. We have px into x plus y minus qy into x plus y equal to y minus x into 2x plus 2y plus z. So here the coefficient of small p, that is capital P, is x into x plus y, and capital Q, the coefficient of the partial derivative of q, dou z by dou x, is minus y into x plus y, and r is equal to y minus x by 2x plus 2y plus z. Therefore, the auxiliary equation is dx by x into x plus y, dy by minus y into x plus y, dz by y minus x into 2x plus 2y plus z. Now, the first two ratios can be comparable. So, comparing these two, dx by x into x plus y equal to dy by minus y into x plus y. Cancelling and simplifying, integrating, dx by x is ln x equal to integral dy by my y is ln y. So, here we have a negative sign, minus ln y plus ln z1. As usual, we have log ln x plus ln y equal to ln z1. So, ln of xy equal to ln z1. So, xy equal to c1. So, this is the first part of the solution. Now, in order to get the second part of the solution, we are applying this so-called above important property, that is, if a1 by b1 equal to a2 by b2 equal to a3 by b3, then a1 minus a2 by b1 or a1 plus a2 by b1 plus b2 is equal to a1 plus a2 plus a3 by b1 plus b2 plus b3. So we are applying that property here. We are adding the first two ratios, that is dx plus dy x into x plus y plus minus, plus means plus into minus, we get minus y into x plus y equal to dx plus dy plus dz by x into x plus y minus y into x plus y plus y minus x into 2x plus 2y plus z. I say once more, we are adding the first two ratios. We get the left side as dx plus dy, adding the numerators dx plus dy by the same process should be done on the denominator also, x into x plus y plus minus y. So minus y into x plus y is equal to, we are taking the right side as the sum of numerator by sum of denominators, dx plus dy plus dz by x into x plus y minus y into x plus y plus y minus x into 2x plus 2y plus z. Now come to the left side, we have dx plus dy. From this we can take x plus y as common factor, so x plus y into x minus y equal to dx plus dy plus dz by, taking from the first two terms we can take x plus y outside, x minus y plus y minus x into 2x plus 2y plus z. That is dx plus dy plus dz divided by, from these two terms, the first one is x plus y into x minus y, the second one is y minus x into 2x plus 2y plus z. From this we can take x minus y as a common factor. So taking x minus y as common factor, the remaining factors are x plus y minus of 2x plus 2y plus z, because minus is because here we have y minus x. We are taking x minus y as common factor. So here we have a negative sign. Now, comparing the left and right sides, we have x minus y is common, so cancel. So what remains on the left side? We get dx plus dy divided by x plus y equal to dx plus dy plus dz divided by x plus y. Now opening the negative sign, we have minus 2x minus 2y minus z. Okay, what is that? It is equal to dx plus dy plus dz divided by x minus 2x is minus x, y minus 2y is minus y, and minus z. That's equal to dx plus dy plus dz divided by, from this we can take minus outside, minus of x plus y plus z. Now taking this negative right side to the left side, we have dx plus dy by x plus y plus dx plus dy plus dz by x plus y plus z equal to 0. Now we can integrate. So for integrating the x plus y in the first term is nothing but the derivative of numerator denominator, here also the derivative denominator. So we are taking the substitution as x plus y is equal to u and x plus y plus z equal to some v. We can write it du by u plus dv by v equal to 0. Now integrating, we have u plus ln equal to ln c2, ln, that is ln of uv equal to ln c2, replace, that is eliminating u, ln uv equal to c2, that is u means x plus y into x plus y plus z equal to c2 in the second part also. Now the required solution is x plus y into x plus y plus z equal to a function of the first part is x into y, so x into y, that is the answer. Now I shall give one homework question, homework. Y plus z x into p minus x plus y z into q equal to x square minus y square. You should get the answer x square plus y square minus z square equal to function of x, y plus z. Another question. If u is a function of x, y, z, which satisfies the partial differential equation y minus z into dou u by dou x plus z minus x into dou u by dou y plus x minus y into dou u by dou z equal to 0, then show that u contains x, y, z only in combination of x plus y plus z and x square plus y square plus z square. That is, if u is a function, u satisfies the partial differential equation, means u is a solution of this equation. If u is a solution of this equation, then u will be of the form of a combination of the functions x plus y plus z and x square plus y square plus z square. Now this is a partial differential equation in 3 independent variables. Here the independent variables are x, y, z. Up to this we have done the questions based on the Lagrange's equation with the 2 independent variables. Here we have the situation that there are 3 independent variables x, y, z. Now let us solve this equation. Our differential equation is y minus z into dou u by dou x plus z minus x into dou u by dou y plus x minus y into dou u by dou z is equal to 0. So in order to solve this equation, we have to write the auxiliary equation, that is dxy, first independent variable by dxy, y minus z equal to dy by z minus x equal to dz by x minus y is equal to du by 0. The right side is 0. Now First, we can compare the last ratio with any one of these. So we are comparing dx by y minus z with du by c. From this we get du equal to 0 means u equal to 0. Now for getting the remaining part of the solution, let us take the Lagrange's multipliers as 1, 1, 1. Then each ratio is equal to dx plus dy plus dz plus dz 1, 1, 0 divided by dx means y minus z plus z minus x plus x minus y plus 0. That is equal to dx plus dy plus dz divided by 0. That implies dx plus dy plus dz equal to 0 implies x plus y plus z equal to c. Second part of the solution. Now we have to get the third part of the solution, because here we have 3 independent variables. The solution should contain 3 functions. Now, for getting the third part of the solution, let's take the multipliers as x, y, z, 0. Then each ratio is equal to x dx plus y dy plus z dz bar plus 0 divided by x into y minus z plus y into z minus x plus z into x minus y. Now that is x dx plus y dy plus z dz divided by 0. As before, if we are opening the brackets, all the terms will cancel each other and we get the value 0. So from this we can therefore we can deduce the result that x dx plus y dy plus z dz is equal to 0. Multiply with the 2 and integrating, finally we get x square plus y square plus z square equal to c. Hence we get the solution. Now, since there are 3 solutions, solution contains 3 functions: u x y z equal to z1, v x y z equal to z2, and w x y z equal to z3. Then the solution of the partial differential equation having 3 independent variables can be written as one of them is equal to function of the others. So we can write u is equal to function of v and w. That is, u equal to v means here x plus function of x plus y plus z and x square plus y square plus z. That is the answer. That is the solution. The first part is u is equal to 0. So one of them is a function of the others. Here we can write u is equal to function of the others. Others means x plus y. That is, we get the answer as. Another question, solve the equation x into dou u by dou x plus y into dou u by dou y plus z into dou u by dou z is equal to au plus xy by z. As usual, this is also a Lagrange's equation of 3 independent variables x, y, z. So in order to solve this equation, what we do? Write the auxiliary equation. So the auxiliary equation is dx by x equal to dy by y equal to dz by z equal to du by au plus xy by z. Now comparing the first and second ratios, we have dx by x equal to dy by y, integrating log x equal to log y plus log z1, log x minus log y equal to log z1, log x by y equal to log z1, that is xy by x by y equal to z1. That is first part of the solution. In a similar way, we can equate the first and the third ratio. We have dx by x equal to dz by z. We will get the solution as x by z equal to z2. Now compare the first and last ratios. We have dx by x equal to du by au plus xy by z. Now from this ratio, we take another ratio as the ratio of numerator equal to ratio of denominators. That is, du by dx equal to au plus xy by z by x. So we get another ratio as like this. That is, a du by dx equal to au plus xy by z by x. Now splitting this ratio, we have a u by x plus xy by z by x. So write it like this. Now x will cancel and we get du by dx equal to au by x plus xy by y by z. Now this is our linear equation in u and x. That is, du by dx minus au by x equal to y by z, which is a linear equation in u and x. So in order to solve this equation, we have to write p. What is p? P is equal to minus a by x. Now integral p dx is integral of minus a by x dx equal to minus a ln x. Now ln x raised to minus a, taking the integrative factor, e raised to integral p dx becomes e raised to ln x raised to minus a equal to x raised to minus a. Therefore, the required solution is u into integrative factor equal to integral of the right side into integrative factor dx, that is u into x raised to minus a equal to integral y by z into x raised to minus a dx. Here the integral variable of integration is x, so y by z is treated as a constant, so take that constant outside, that is y by z into integral x raised to minus a. So how to integrate this one? Here we can apply this rule, that the rule is integral x raised to n dx is x raised to n plus 1 by n plus 1 because minus a is constant. So what we get? It is equal to y by z into x raised to minus a plus 1 by minus a plus 1 plus the constant of integration, that is c3. Now taking this one to the left side, we have u x raised to minus a minus y by z into x raised to 1 minus a by 1 minus a equal to c3. Therefore, the required solution is phi of x by y comma x by z comma u x raised to minus a minus y by z x raised to 1 minus a by 1 minus a equal to 0. Since the solution, we should write y of c1, c2, c3 equal to 0. c1 is x by y, c2 is x by z, c3 is this one, so equal to 0. Hence, we have completed the solving methods of linear partial differential equation. Now let us go to the last section of this chapter, that is the geometrical interpretation of the Lagrange's equation. That is, we know the Lagrange's equation is Pp plus Qq equal to R. P, Q, R are functions of x, y, z, and we will, for after solving, we will write the solution as phi of uv equal to 0, where u being a function of x, y, z equal to c1 and v and the function of x, y, z equal to c2 are the solution of the auxiliary equation dx by p equal to dy by q equal to dz by r. Geometrically, the solution, that is phi of uv equal to 0, this will represent a family of surfaces in space. That is, the solution of the Lagrange's equation will represent a family of surfaces in space, and this family of surfaces is called integral surfaces. Because it is a family of surfaces, because we are writing as phi changes, we will get a family of surfaces in space, and this surface is called integral surface. Now this u equal to c1 and v equal to c2 are the solution of the auxiliary equation. So geometrically, u equal to c1 and v equal to c2 will represent a family of curves which are the solution of auxiliary equation. Family of curves that lie on the above surfaces, and this family of curves is called integral curves. So we can write the definition of integral surfaces and integral curves. The integral surfaces are First we write the definition for integral surfaces. The integral surfaces are the solution of the Lagrange's equation Pp plus Qq equal to R, and the general form of this integral surface is phi of uv equal to 0. Next we write the definition of integral curves. The integral curves are the solution of the auxiliary equation dx by p equal to dy by q equal to dz by r of the Lagrange's equation. Auxiliary equation of the Lagrange's equation Pp plus Qq equal to R, and the general form of that equation, general form of the equation to the integral curves is u equal to c1 and v equal to c2 and v equal to c2. So next we shall find the integral surface through a given curve. integral surface through a given curve. That is, here we have given a partial differential equation representing the family of integral surfaces, and we have to find from that family of integral surfaces, we have to select one of them as a surface which is passing through a given curve. So in order to find that surface, we adopt 3 steps for finding such integral surface. That is, the situation is, we have given a partial differential equation Pp plus Qq equal to R, and we have given a curve C, say a function of x, y, z equal to 0. We have to find an integral surface passing through this curve. What we do is, on step 1, we should find the solution of the corresponding auxiliary equation u equal to c1 and v equal to c2. These are the solution of, these are the integral curves. Phi of uv equal to 0 is the family of integral surfaces. So first we find the solution of the given solution of the auxiliary equation of the given differential equation. Now, after finding u equal to c1 and v equal to c2, let us go to the step 2. On step 2, what we do is the parameterization of the given curve through which the surface passes. So in order to parameterize the given curve C, what we do is, we are taking any one of the variable x, y or z as some t. Say for example, suppose we are taking x equal to t, then from the given curve, equation to the curve, we parameterize that as the remaining 2 variables y and z in terms of t. Hence, we get C as a function of t alone. That is the parameter equation to the given curve. Now we are discussing how to find the integral surface through a given curve, the working method. Integral surface through a given curve. Given curve, say C. Step 1. Solve the Lagrange's equation Pp plus Qq equal to R. We get u equal to z1 and v equal to c2. That is, on step 1, we find the solution of the. Let us go to the working method of finding an integral surface of the differential equation Pp plus Qq equal to R passing through a given curve. So step 1, solve the Lagrange's equation Pp plus Qq equal to R. U equal to c1 and v equal to c2 be the solution of the auxiliary equation dx by p equal to dy by q equal to dz by r. That is, first we find the solution of the auxiliary equation and put it as u equal to v1 and v equal to c2. Then step 2, parameterize the given curve. Parameterize the given curve. Given curve C in terms of t. For this, we should start from either taking x or y or z as t, then replacing all other variables in terms of t, we will get the parameterization. So on step 2, we have to parameterize the given curve C in terms of a parameter t. Then step 3, here we substitute the parameterized curve C on u equal to z1 and v equal to c2. That is, we have to apply the parameterized form of the curve C on the equation u equal to z1 and v equal to c2. Then we will get a relation connecting c1 and c2 by eliminating t. At last, replace c1 and c2 by u and v, we get the required integral surface. So let us go to an example. Find the integral surface. Find, first example, find the equation of the integral equation of the integral surface of the differential equation x into y minus z plus into p plus y into z minus x into q equal to x minus y into z, which passes through the curve x equal to y equal to z. So this is the question. You have to find the integral surface of this differential equation which passing through the given curve. Here the differential equation is x into y minus z into p plus y into z minus x into q equal to x minus y into z. First we solve this equation. For that we will write the auxiliary equation x into y minus z equal to dy by y into z minus x equal to dz by x minus y into z. Now we cannot compare these equations. We apply the Lagrange's multipliers method. So the first one we choose the multipliers as 1, 1, 1. Then each integrative factor is ratio is equal to dx plus dy plus dz by x into y minus z plus y into z minus x plus z into x minus y. The denominator is 0. Therefore numerator is also equal to 0. So integrating we will get the first part of the solution equal to C1. So this is our use. Now taking the next set of Lagrange's multipliers as 1 by x, 1 by y, 1 by z, we can write each ratio is equal to 1 by x dx plus 1 by y dy plus 1 by z dz divided by 1 by x into x. So it becomes y minus z plus 1 by y into y. It becomes z minus x plus 1 by z into zx minus y. Z cancel and we had x minus y. Here also the denominator is 0. Therefore 1 by x dx plus 1 by y dy plus 1 by z dz is equal to 0. Integrating we will get ln x plus ln y plus ln z equal to ln c2 means xy z equal to c2. So this is our B. So we have the integral curves. Integral curves are the solution of auxiliary equation. So we have the solution of the auxiliary equation as u equal to c1 and v equal to c2. So this will represent integral curve as u means x plus y plus z equal to c1 and xy z equal to c2. So these are the integral curve. Now the given curve C is x equal to y and x equal to y equal to z. So next step is parameterize this curve. So for parameterization, for parameterizing C, we put x equal to t. Since x equal to y, we have y equal to t. Since x equal to y equal to z equal to t. So all variables are parameterized as t. Now we substitute this parameterization in step. We have t plus t equal to c1. That is 3t equal to c1. T into t equal to c2 means t cube equal to c2. So these are the new equations. This is 3, this is 1. Now eliminate t. So equation 3 we get a t equal to c1 by 3. Now substitute in 4 we get t cube means c1 by 3 whole cube equal to c2. So c1 cube by 27 equal to c2. So c1 cube equal to 27 c2. Now replacing c1 and c2 as in star, the required integral surface is c1 cube. What is c1? X plus y plus z whole cube equal to 27 xy z. So this is the answer. So I hope all of you understand this method. Now we can do another question. See. Find the integral surface. Integral surface of 2y into z minus 3 into p plus 2x minus z into q equal to y into 2x minus 3, which passes through x square plus y square equal to 2x, z equal to 0. So, answer. The auxiliary equation is dx by 2y into z minus 3, dy by 2x minus z, dz by y into 2x minus 3. Now we can compare the first and last. We have dx by 2y into z minus 3 equal to dz by y into 2x minus 3. Y cancelled, cross multiply. So this can be made into variable separable form. So for that multiply the cross multiplying 2x minus 3 dx equal to 2z minus 3 into dz, integrating 2x integral becomes x square minus 3x equal to 2z becomes z square minus 2 into 3 6 into z plus c1, that is x square minus 3x minus z square plus 6z equal to c1. Put it as equation 1. Now we cannot compare the remaining ratios, so we are choosing the multipliers as 1 2y minus 2. We have each ratio equal to 1 into dx plus 2y into dy plus minus 2 into dz divided by 1 into, so 2y into z minus 3 plus 2y into 2x minus z plus minus 2 into y into 2x minus 3 equal to dx plus 2y dy minus 2 dz divided by opening, we have 2yz minus 6y plus 4xy minus 2yz minus 4xy plus 6y. So 2yz, 4xy, 6y cancelling, we get 0. Therefore dx plus 2y dy plus minus 2 dz equal to 0. Integrating, we get x plus y square minus 2z equal to c. So writing these 1 and 2 together, we can write x square minus 3x minus z square plus 6z equal to 0. X plus y square minus 2z equal to 0. So these are equation to integral curves. Okay, now we have to parameterize the given curve. The given curve is x square plus y square equal to 2x, comma z equal to 0. Already z equal to 0. Now put x equal to t. We have y square equal to 2x minus x square means 2t minus t square. Hence the parameterization for c is c, x equal to t, y equal to root of 2t minus t square, and z equal to c. Then next we substitute this relation in equation in u equal to c1 and v equal to c2. So substituting, we have in star. This is our equation star. In star we have x square. X square means t square minus 3t minus z square is 0 equal z square plus 6z is again 0 equal to c1, and x t plus y square. Y square is 2t minus t square, then minus 2z is 0 equal to c2, that is t square minus 3t equal to c1, 3t minus t square equal to c2. Now for eliminating t between these two equations, this equal and opposite, so we are adding this, we can eliminate. So adding, we have t square minus 3t plus 3t minus t square equal to c1 plus c2. So cancelling all, we have c1 plus c2 equal to c2. So this is the equation that we obtained by eliminating t. Now finally replace c1 and c2 by u and v. Therefore the required integral surface is c1 plus c2, x minus x square minus 3x minus z square plus 6z, that is our c1, plus c2. c2 is x plus y square minus 2z equal to 0. Now we can write it as x square minus 3x and 2x will give minus x plus x and will give 2x, then y square minus z square, 6z and minus 2z will give plus 4z equal to c. Right? Now let us go to another important question. 2xy minus 1 into, find the integral surface through 2xy minus 1 into p plus z minus 2 x square into q equal to 2 into x minus yz. It's passing through x equal to 1 comma y equal to 0. So the auxiliary equation is 2xy minus 1 dy by z minus 2x square dz by 2 into x minus yz. Now comparison method is not possible. So we are choosing the multipliers as 2x, 2y, 1. We have each ratio is equal to 2x dx plus 2y dy plus dz by 2x into 2xy minus 1 plus 2y into z minus 2x square plus 2 into x minus yz. That is equal to 2x dx plus 2y dy by plus dz by, opening the brackets in the denominator, we have 4x square y minus 2x plus 2yz minus 4x square y plus 2x minus 2yz. So all which cancelled. So 2x dx plus 2y dy plus dz by 0 means 2x dx plus 2y dy plus dz equal to 0. Then integrating, we get x square plus y square plus z equal to 0. Similarly, we choose the next set of multipliers as, choose the multipliers as z1x. We get each ratio equal to z dx plus dy plus x dz by z into 2xy minus 1 plus z minus 2x square plus 2x into x minus yz. We can open in the brackets and we can see that all terms in the denominator is equal to 0. Therefore, z dx plus dy plus x dz equal to 0. So integrate. Now rearranging z dx plus x dz together plus dy equal to 0. That is, this is nothing but d of xz plus dy equal to 0, which is an exact equation. And integrating, we will get the solution as, xz plus y equal to c2. Now, parameterizing the given curve. The given curve is nothing but x equal to 1, y equal to 0. So we can substitute this in c1 and c2. c1 becomes x equal to 1 plus y equal to 0, z equal to x equal to 1, y equal to 0, and z equal to z. So z equal to c1, x equal to 1, so z plus 0 equal to c2. So eliminating z between these, we have 1 plus c2 equal to c1. Therefore, the required integral surface is 1 plus c2. c2 means xz plus y equal to c1 means x square plus y square plus z. So in this way, we can find the integral surface through a given curve. So we can do some homeworks questions. First one, find the integral surface of AP plus BQ equal to 1, which passing through the curve x square plus y square equal to 1, z equal to 0. The answer is x minus kz whole square plus y minus bz whole square equal to 1. Now the second one, find the integral surface of x minus y into y square p plus y minus x into x square q equal to x square plus y square into z, which passes through x is equal to a cube, comma y equal to 0. You should get the answer. Answer is q into x cube plus y cube whole square equal to a raised to 9 into x minus y whole cube. Now the last question, find the integral surface of x cube p plus y into 3x square plus y into q equal to z into 2x square plus y, which passes through y square equal to z minus y and x equal to 1. So the answer, x cube plus y into x z minus y equal to y z. So hence we come